Hi there everyone, welcome back to my channel. In this video, we will be continuing our understanding in alkanes, alkenes, and alkynes, and expanding our knowledge on hydrogenation and hydration reactions. This includes drawing the line angle structure, showing a hydrogenation reaction by adding H2 with the correct catalyst, and showing a hydration reaction by adding H2O with the correct catalyst, and the products of both reactions. Today's example is 3,3-diethyl-1-hexene. Before we jump in, let's quickly review what we know about alkanes, alkenes, and alkynes. From the previous video, we know about alkanes. Alkanes are organic compounds containing carbon and hydrogen. As we know, they are presented something like this, a sort of a zigzag line structure. We know that alkanes only have a single bond between carbon atoms. Alkenes have a double bond between one of the carbon atoms, and alkynes have a triple bond between one of the carbon atoms. To solve this problem, we also need to be familiar with the first 10 alkanes. Most prefixes of each of these names correlates with a specific number. However, alkanes 1 through 4 are different, considering their prefixes aren't correlated with a number. So we must pay more close attention to those alkanes. If you need more clarification on this topic, you can watch my last video. We also refer to our list of substituents in this video. Remember, these are legs that hang from the line angle structures. Here's a list that we will refer to in our problem. Now, let's go through the process of drawing the line angle structure of this molecule, 3,3-diethyl-1-hexene. Remember our first rule when we're looking at molecular structures like this. We know that we always start at the end of the name. In this compound, hex, right here, tells us that there are 6 carbons present in the longest carbon chain. We know this because looking back at our alkanes list, we see hexane, and hex means 6. For this part, we see ene at the end. Let's defer back to our alkane, alkene, and alkyne list. Here we see we have alkanes, alkenes, and alkynes. But which one do we have in our molecule? Looking back, we see ene. Looking backwards, we see that alkenes has the same ending as ene, so therefore we have an alkene. Because we have an alkene, this means that our molecule will have a double bond between one of the carbon atoms. Now we can take away that from the ene in hexene, we see that we have an alkene, or 2 bonds. So this means that we need a double bond on our molecule. When we draw the 6 carbons in a line structure, it looks something like this. Since we see the number for our double bond, 1, we know that we place it at the first carbon. So we know our double bond is placed right here. Our bond is present between the first and second carbon, so our double bond looks like this. Referencing back to our substituent list, we see ethyl, and we know that there is 2 ethyls present given the prefix di on the hexene. So we see that we have 2 ethyls present on the third carbon on the hexene. Here we see that we have the numbers 3, 3. This means that we have 2 ethyls present on the third carbon. So let's draw what that looks like on our structure. Here's our completed structure that is 3,3-diethyl-1-hexene. Now let's show a hydrogenation reaction by adding H2 with the correct catalyst and show our correct product. In reactions, when we see the word hydrogenation, we know that we need to add hydrogen, or H2, to our compound, or in this case, to our alkene. For a little review, hydrogenation is the addition of H2 to an alkene in the presence of a metal catalyst, often platinum, palladium, and nickel. With catalyst, it does not matter which catalyst is present, just as long as there is a catalyst present in the reaction. The catalyst does not affect the energy of your reactants or of your products. It's still the same energy for both of those. The catalyst decreases the necessary activation energy, which increases the rate of your reaction. So, if we were to pick a metal catalyst to speed our reaction, let's pick palladium. Here, we have our alkene. We see that it's going to be plus H2, which is 2 hydrogens. All we must do is get rid of the double bond on our alkene. What happens is that these 2 hydrogens are attracted by the electrons in the bond, and as a result, they go on either side of the double bond. In short, and to make it easier, we just need to get rid of our double bond on our alkene. So, this would be our correct product of the hydrogenation of 3,3-diethyl-1-hexene. Lastly, let's show a hydration reaction by adding H2O with the correct catalyst and showing our correct product. In reactions, when we see the word hydration, we know that we need to add water, or H2O, to our compound, or in this case, to our alkene. For a little review, a hydration reaction is the addition of H2O to an alkene in the presence of an acid catalyst to make an alcohol. So we know that we must add H+, our acid, to our alkene. Remember, water can be thought of as H2O or HOH. This is still water, but we can draw it this way to help gain a better understanding of the products in this hydration reaction. Just like in a hydrogenation reaction, the molecules are added to one side of the bond, and the other is added to the other side of the bond. Here we have our alkene being added to H2O, and first we will get rid of our double bond on our alkene and add OH on one particular side. But how do we know which side to put the OH on? Well, we must follow the rule known as Markovnikov's rule. This rule means that the carbon with the most hydrogen gains the hydrogen. We remember this by the phrase, "the rich get richer." First, let's get rid of our double bond and write our basic structure. So, we see here at the first carbon, we see that it has 2 carbon-carbon double bonds, and so to get to 4 bonds, that means it needs 2 more hydrogens. On the second carbon, it has 3 bonds going to it, so it's just going to need 1 hydrogen. After this explanation, we see that the H is going to the side with more hydrogens, so in this case, the hydrogen is going to go to the first carbon. Because of this, we know that the OH is going to the side with the least amount of hydrogen, which is the other side, so the OH is going to go to the second carbon. So we got rid of our double bond, and now let's add our OH group to the second carbon. Let's not forget to add our substituent groups to where they belong. So this would be our correct product of the hydration of 3,3-diethyl-1-hexene.